So, when we consider periodic behavior of atoms, what is it that we should really consider, and how should we determine differences in different atoms' behaviors? Well, primarily the most important thing to consider is what is the valence level of the atom? Because, of course, if an atom has a valence level of 7 compared to another atom that has a valence level of 1, well, the electrons that in a sense govern the atom's behavior, the valence electrons, are much farther from the nucleus if they're in the 7th level than the 1st. And so there's going to be far less nuclear governance of those electrons, control of those electrons. The second thing you'd want to consider, however, and you should do so sequentially, valence level typically plays the greatest role in why an atom does what it does. But the second most important consideration is effective charge. What is the effect that the nucleus has on the valence electrons? Greater effect is going to result in a different behavior of an atom than if there's less of an effect on those valence electrons. Last and least, but still it plays a role in some situations, it's the actual number of valence electrons that plays a role in determining behavior of atoms. And what I want to do is, as I go through and consider certain types of periodic behaviors, which we're going to do, I want to think in this sequence. I want to think, what is the valence level first? What is the effective charge of the two atoms' nuclei second? And last and least, if it comes down to that, I'll consider how many valence electrons there are. Now, as our first periodic behavior that we want to discuss, and we no longer need this, we're going to consider atomic radii. What happens to the radius of an atom as you move either across a period or down a group? And the simplest thing to consider is two atoms in the same group. Compare them. For instance, let's randomly choose oxygen from group 6 and selenium from group 6. Oxygen versus selenium. Ding ding! In this corner, weighing in at atomic number 8 and 16 atomic mass units, we have oxygen. From Schenectady, Illinois, weighing in at a much higher mass, we have selenium. Which of these atoms would have a larger radius, and why would it be a larger radius? Well, the first thing I'd want to consider is, of course, what the valence levels are. And, well, I should back up a second and first make sure I know what a radius is. And yes, we know a radius for a circle is the distance from the center of a circle to the periphery, the edge of the circle. But when we're talking about atoms, the thing at the center is, of course, the nucleus. And the edge is defined by the valence electrons. And what principal energy level are the valence electrons? So, of course, the radius of an atom is the distance from the center of the nucleus of that atom to the valence level electrons of that atom. So, it's going to make my job fairly easy. If the atoms are in the same group, there's only one difference. They have the same number of valence electrons, and they have the same effective charge. We learned that on the preceding video. But the big difference is they have different valence levels. Oxygen is in the second period, so its valence level is N equals 2. Selenium is in the fourth period, so its valence level is much higher. It's the fourth principal energy level. So, of course, it makes absolute sense that selenium, due to the fact it has a higher valence level than oxygen, must have a larger radius, and that is the truth. And that's the explanation you want to use when you discuss atoms in the same group. The one having the larger radius will always have the higher valence level, and the one having the smaller radius would always have a lower valence level. So, what happens instead if we consider atoms in the same period? For instance, let's pick carbon and compare it to oxygen. Well, give myself some space down here. Carbon versus oxygen. Here I'd want to look at the configurations. Carbon has helium's core, 2 2s2, 2p2 as its valence configuration. Oxygen also has helium core, 2s2, 2p4. Now, clearly, they're both period 2 elements. They both have the same valence level. That's not going to help me determine who has a larger radius. So the next thing I would consider is effective charge. Now, I don't really need, as we've already figured out yesterday, for neutral atoms to write their configurations to figure effective charge. I know the effective charge of carbon is +4 because it's a group 4 atom, and oxygen's effective charge is +6 because it's a group 6 atom. And so necessarily, I think, what does that mean? Well, if the atom has a greater effect on the second valence level electrons, or the valence level electrons in the second principal energy level, it's going to draw them in more tightly, closer to the nucleus. You see, carbon has less of an effect on these valence electrons, so they tend to be farther away from the nucleus. And therefore, I would say that carbon, by virtue of the fact it has a lesser effect on its valence electrons, has a larger radius. And helium, because it has oxygen, because it has a much greater effective charge, a greater effect on its valence electrons, has a smaller radius. So an interesting phenomenon happens as you move left to right through a period. You actually see a decrease in radius with each successive atom. And that's very counterintuitive because, of course, lithium is a much smaller atom in terms of mass than neon. After all, lithium only has 3 protons and 3 or 4 neutrons in its nucleus, and neon has 10 protons and 10 or more neutrons in its nucleus. It's a far more massive atom than lithium, and yet despite all that greater mass, it has a much smaller radius than lithium, and that's because effective charge steadily increases as you move across a period. +1, +2, +3, 4, 5, 6, 7, 8. So the atoms on the right side have the greatest effective charge in their period, and the ones on the left side have the least effect on their valence electrons. So radius steadily shrinks left to right, and it steadily shrinks bottom to top because that's the valence level argument. You have a lower and lower level of valence electrons closer to the nucleus. That means that helium is the neutral atom with the smallest radius. It has only n = 1 as a valence level, and it has the biggest effective charge in its period. And it means francium is the element with the largest radius because, of course, its valence electrons are way up in the 7th energy level, and it has a very weak +1 effect on that valence electron. So you may be wondering, well, when do we ever get to the number of valence electron argument? Well, that would be the case if we were to compare, say, chlorine, the neutral atom, and chloride, the anion of that neutral atom. Because chlorine has neon's core and a 3s2, 3p5 configuration for its valence electrons. Chloride, the ion, has the same core, but it has one more valence electron than chlorine. This is chlorine, this is chloride. And so, of course, if I went through my list of considerations, first consideration, valence level. Both atoms have the identical valence level, n = 3. That's not going to help me determine who has a larger radius. So then I consider the effective charge. Well, both chlorine and chloride have an effective charge over their valence electrons of +7. And that's because in both cases they have 17 protons, and in both cases they have 10 shielding electrons blocking the valence electrons from being pulled toward the nucleus. So in both cases, 17 minus 10 is +7. So I still see no difference based on effective charge. So the last consideration you revert to, if there are no other differences, is how many valence electrons there are. And in this situation, that's the only difference. In the case of chloride, there are 8 valence electrons. In the case of chlorine, there are only 7 valence electrons. And you're saying, well, how would that affect radius? Quite simply, if there are 8 valence electrons and electrons repel each other, there is greater electron repulsion amongst the valence electrons in chloride. Because of that additional electron, there are more of them, and they repel each other more. Greater electron repulsion amongst the valence electrons. Chlorine has less of an electron repulsion between these 7 valence electrons than we'd see between these 8 valence electrons. Now, when electrons repel each other, they push apart from one another. And of course, there's only one direction electrons out in the valence level can be pushed. They're not going to be pushed down into lower energy levels because those are already occupied by electrons. So when these guys get to shoving each other out of the way, they're going to push outward. So now I have the answer in terms of radius, because the only difference between these two atoms is that the anion has greater electron repulsion because it has more valence electrons to repel each other. They're going to spread themselves outward more than these 7 valence electrons would, and that necessarily means that chloride would have a larger radius than chlorine. Now, don't be fooled by cheap imitations, as they like to say. Just because neutral atoms and anions have a different argument to explain their different radii doesn't mean that we need a fourth argument if we're going to try and compare neutral atoms to their cations. That's just one of the preceding arguments. Because if you consider calcium a period 4 atom, its valence level is n equals 4. However, the cation forms by being oxidized twice. The calcium atom gets oxidized twice. And the 2 electrons it loses are its valence electrons, meaning the valence level of calcium cation is n equals 3. It has the same configuration as argon, and therefore its valence level is n equals 3. And so consequently, this argument is simple. The cation of calcium has to have a smaller radius than calcium because calcium has a higher valence level, and that's our first consideration always, is valence level. And because the calcium atom has n equals 4, a higher valence level than the calcium cation that has a valence level of n equals 3, the calcium atom would have the larger radius. Now, in the next video, part 3 of the periodic behavior videos, I'm going to do a bunch of examples and explain what you should write by way of answers for these examples if you're asked to explain who has a larger radius and why.